3i Atlas is now, carrying a swarm of unknown objects, and scientists can't fully explain it. There's something riding through our solar system right now. An interstellar visitor, one that came from the void between stars, has developed a tail that points in the wrong direction. Not backward from the sun as physics demands, but forward, straight into the solar wind like a knife cutting against the current. That tail, glowing faintly in telescopic images captured just weeks ago, shouldn't exist according to every model we have of how comets behave. And yet there it is, sharp and persistent, defying the rules. But here's where it gets unsettling. A growing number of researchers now believe that tail isn't just an optical trick or a quirk of dust geometry. It's a swarm of unknown objects travelling ahead of the main body, bound by gravity, glowing from reflected sunlight off solid surfaces we cannot yet resolve. This is 3i Atlas, the third confirmed interstellar object ever detected passing through our cosmic neighbourhood, and it's rewriting the playbook on what we thought visitors from beyond could carry with them. Imagine for a moment that you're staring at an image taken by one of the world's most powerful observatories. You see a bright nucleus, the comet's heart, and stretching away from it in the expected direction is a classic dust tail, faint and fuzzy, blown back by solar radiation. But then your eyes catch something else. Another structure, narrower, brighter, pushing forward into the sun sharp as a spear. Your brain stumbles because nothing in your experience of comets prepares you for this. Every tale you've ever seen, every educational diagram you've studied shows material streaming away from the sun, not toward it, and yet this one refuses to cooperate. It sits there in the data, undeniable, reproducible across multiple observation runs, calling into question decades of settled science about how interstellar objects behave. Now here's the question that keeps astronomers awake at night. What if that forward-pointing glow isn't a tail at all? What if it's a cloud of separate objects, fragments, chunks, maybe even intact bodies, clustered together by the comet's weak gravity as it hurtles through space at tens of thousands of miles per hour? What if 3i Atlas isn't travelling alone but is dragging a retinue of unknowns with it, a procession of material that predates its arrival in our solar system, possibly older than our sun itself? This isn't science fiction. This is the hypothesis now circulating among leading astrophysicists, and it's based on observations you can verify yourself if you have access to the right telescopes and image processing software. The anti-tail of 3i Atlas, that's the term scientists use for this anomaly, has been imaged multiple times through late November and early December, and each new photograph deepens the mystery instead of resolving it. You have to understand how rare this situation is. Interstellar objects don't visit often. We've confirmed exactly 3 in human history: Oumuamua in 2017, Borisov in 2019, and now 3i Atlas in late 2025. Each one has challenged our assumptions. Oumuamua tumbled through without any visible tail, sparking wild debates about whether it was a comet, an asteroid, or something we had no category for. Borisov looked comfortably normal, a textbook comet with predictable outgassing and a well-behaved tail. But 3i Atlas? It's sitting somewhere between the two, exhibiting comet-like activity, jets of gas brightening near the sun, while simultaneously displaying this forward structure that has no business being there, and the timing couldn't be more critical. Right now, as you're hearing this, 3i Atlas is making its closest approach to Earth in its entire journey through our solar system. Observatories around the globe are training their instruments on it, collecting data at a pace we've never achieved with an interstellar visitor before. This is a live investigation, unfolding in real time, and the swarm hypothesis is only gaining traction as more images come in. Let me paint the stakes clearly for you. If 3i Atlas is indeed carrying a swarm of objects, whether natural fragments or something else entirely, we're not just looking at a comet. We're looking at a delivery system from another star system, a capsule carrying samples of material forged under alien suns, tempered by radiation we'll never experience on Earth, and now drifting within reach of our best instruments. Every chunk in that swarm, if it exists, is a messenger from deep time and deep space. Analysing even one of them could teach us more about stellar evolution, planetary formation, and the diversity of cosmic environments than 100 theoretical models. But there's a darker edge to this excitement, one that responsible scientists are beginning to voice more openly. What if we don't know what we're looking at? What if our models are so tuned to objects born in our solar system that we're blind to the signatures of something genuinely foreign. We've had exactly 3 chances to study interstellar visitors up close, and each time we've been caught off guard by their behaviour. Oumuamua showed non-gravitational acceleration without detected outgassing. Borisov showed unusual activity patterns. Now 3i Atlas is glowing in the wrong direction. Pattern recognition is a survival instinct, and right now that instinct is screaming that we're missing something fundamental about how matter behaves when it crosses the interstellar void. Stay with me here, because in the next stretch of this video, we're going to unpack exactly why leading experts are saying this interstellar guest might be carrying a swarm of unknown objects, what those objects could be, and why the answer matters far beyond astronomy. We're going to walk through the evidence step by step, weigh the competing explanations, and confront the uncomfortable possibility that our solar system is hosting something we don't have the language to describe yet. This isn't hype. This is careful science meeting honest mystery, and you're going to see both sides of that conversation laid out in full. But before we dive into the deep analysis, I need you to do something for me. If this mystery chills you the way it does me, if the idea of a swarm of unknowns riding through our solar system makes your pulse quicken even slightly, hit that like button right now. Not for the algorithm, but as a signal. Every like on this video is a data point showing that people care about these questions, that there's an audience willing to engage seriously with cosmic mysteries without demanding easy answers. It tells observatories around the world that public interest in interstellar objects is real and sustained, which matters when research funding is allocated and telescope time is scheduled. And then drop a comment telling me where you're watching from, your city, your country, your corner of this planet, because right now, as 3i Atlas streaks past Earth, we're all witnesses to the same event, separated by borders and time zones, but connected by the fact that something from beyond our solar system is close enough to study, and we're all asking the same question. What is it carrying? And why does it glow where it shouldn't? Your voice in the comments becomes part of the collective record of this moment, a timestamp of when humanity first seriously considered that interstellar visitors might not travel alone. So go ahead, like, comment, and then settle in, because what we're about to explore will change how you think about the space between stars and what might be drifting through it right now. Now let's begin at the beginning, with the facts everyone agrees on before we venture into the territory where scientists start disagreeing, because that's where the real story lives. The facts are simple, verifiable, and undisputed across every major observatory that has trained instruments on this object. 3i Atlas is an interstellar comet. Its trajectory proves it beyond any reasonable doubt. When astronomers plot its orbit backward, the math doesn't curve it around our sun in a neat ellipse like the comets we're used to. Instead, the path traces back out into deep space, toward the galactic plane, implying an origin somewhere in the vast wilderness between stars. It's moving too fast to have been born here. The velocity and angle of approach are the signatures of something that fell into our solar system from outside, drawn by the sun's gravity but not captured by it. It will pass through, swing around, and leave, never to return. That's what interstellar means in this context. A one-time visitor, a traveller passing through a neighbourhood it doesn't belong to, observed only because we happened to be watching the right patch of sky at the right moment. The discovery itself came in the final months of 2025, when automated sky surveys flagged a new object moving against the background stars. Initial observations showed nothing extraordinary, a faint dot, possibly another asteroid or comet from the outer solar system making an unremarkable trip sunward. But as more data accumulated, the orbit calculations started throwing up red flags. The eccentricity was too high. The velocity didn't match anything gravitationally bound to the sun. Within days, the classification changed from routine to extraordinary. This was interstellar. The third confirmed object of its kind, and only the second with clear comet-like features. That confirmation triggered a global response. Observatories from Chile to Hawaii to South Africa began scheduling observation time. Amateur astronomers with advanced setups coordinated imaging campaigns. Space-based telescopes adjusted pointing schedules to capture this visitor during its brief window of visibility, and the data started pouring in. What the data revealed was an object behaving much like a standard comet in many respects. As 3i Atlas approached the sun, it began to brighten, not just from reflected sunlight, but from internal activity. Jets of gas and dust erupted from its surface as solar heat penetrated the etheric nucleus, causing volatile materials to sublimate and vent into space. Spectroscopy confirmed the presence of water vapor, carbon monoxide, and other molecules we associate with comets born in our own solar system. The nucleus itself appeared to be several miles across, large enough to sustain this outgassing for weeks or months as it rounded the sun. A classic dust tail formed, stretching away from the sun in the expected direction, illuminated by sunlight scattering off microscopic particles blown free by radiation pressure. For a moment it seemed like 3I Atlas would be the normal one, the interstellar visitor that finally fit our models without demanding revisions to textbooks. But that moment didn't last. Antitail, first noted in late October imaging, became prominent post-perihelion, its closest point to the sun. Observers began noticing asymmetries in the brightness distribution around the nucleus. Some images showed what looked like a secondary structure extending not away from the sun but toward it, a faint spike of light that didn't behave like the main dust tail. At first, this was dismissed as an artifact of image processing, a trick of stacking multiple exposures where slight alignment errors can create phantom features. But as independent observatories captured the same structure, dismissal gave way to curiosity. The spike was real, reproducible, and persistent across observation sessions separated by days. It wasn't noise, it wasn't a glitch, it was something physical, something attached to or associated with 3I Atlas, and it pointed in the wrong direction. By late November, as the comet made its closest approach to Earth, passing within a distance that allowed for unprecedented resolution, the strange forward glow became the dominant topic in the astronomical community. High-resolution images revealed that this antitail, as it was now being called, was not a diffuse haze but a relatively sharp feature, narrow compared to the main dust tail, and significantly brighter than it had any right to be if it were simply an optical illusion caused by viewing angle. The geometry didn't support the easy explanations. Antitails do appear occasionally on comets, when Earth's position relative to the comet allows us to see edging through the comet's orbital plane, creating the illusion of a tail pointing sunward, because we're looking through a dense sheet of dust from the side. But in the case of 3I Atlas, the math didn't work out cleanly. The angle was wrong, the brightness was wrong, the persistence across multiple observation nights was wrong, something else was going on. And then the speculation began. At first quietly, in private communications between researchers reviewing the data, and then more publicly as preprints started circulating and press inquiries came in. The antitail wasn't behaving like dust arranged in a favourable geometry. It looked more like discrete objects, solid material, possibly clustered, reflecting sunlight more efficiently than gas-blown particles could. The sharpness suggested structure, not diffusion. The stability suggested gravitational coherence, not random dispersion. Observers started using words like swarm and cloud and cluster, terms that implied a collection of separate bodies rather than a continuous tail. And that's when the conversation shifted from documenting an anomaly to questioning what, exactly, was travelling with this comet from another star. Right now, as you hear this, 3I Atlas is moving away from the Sun and away from Earth, but it's still within range of our most powerful telescopes. The window for close observation is narrowing by the day. Every night that passes without capturing detailed images is a night of lost data, lost resolution, lost opportunity to answer the most basic question. Is the antitail a trick of dust and light, or is it a swarm of unknown objects gravitationally bound to the comet's nucleus? This isn't a question we'll resolve with theory alone. It demands data, high-resolution imaging, spectroscopy, maybe even attempts to resolve individual objects within that forward glow if they exist. The urgency is real, the clock is ticking, and the astronomical community knows it. That's why observation campaigns are being coordinated around the clock, why telescope time that was previously allocated to other projects is being reassigned, why researchers are pulling late nights and sharing raw data in real time, rather than waiting for peer review. Because if there's a swarm out there, and if we can study it before 3I Atlas disappears back into the interstellar dark, we'll have learned something profound about what travels between stars and how such objects hold together across cosmic distances. But understanding why this matters, why a swarm hypothesis is both scientifically plausible and deeply unsettling, requires us to first understand why that antitail shouldn't exist in the first place, and that's where we turn next. Let's start with the basics of comet tails, because once you understand how they're supposed to work, the wrongness of 3I Atlas's forward glow will hit you immediately. Comets are dirty snowballs. That's the phrase astronomers love, though it's a bit reductive. They're chunks of ice mixed with rock and organic compounds, leftovers from the formation of planetary systems, preserved in the deep freeze of the outer solar system or interstellar space for billions of years. When a comet swings close to a star, solar heat penetrates the surface, causing ices to vaporize. This outgassing carries dust particles with it, and both the gas and the dust form tails. But here's the critical part. Those tails always point away from the sun. Always. Not because the comet is moving backward, but because the sun's radiation and solar wind physically push the material away. Light exerts pressure. The solar wind, a stream of charged particles flowing outward from the sun at hundreds of miles per second, exerts even more. Gas molecules and tiny dust grains are light enough to be shoved directly away from the star, creating the spectacular tails we see in photos, sometimes stretching millions of miles into space. The tail doesn't follow the comet's motion, it follows the direction of the sun's push. This is first-year astronomy, textbook material, observed in every comet we've ever studied. So when you see a tail pointing toward the sun, your brain should rebel. It's like watching water flow uphill. It violates the basic physics of radiation pressure and solar wind interaction. And yet, 3I Atlas has exactly that. A structure extending from its nucleus in the direction of the sun, bright enough to show up in multiple images, stable enough to persist across observation sessions. The immediate question is, how? How does material defy the outward push and instead glow sunward? The first answer astronomers reach for is the antitail explanation, a known phenomenon that can create the illusion of a sunward tail under specific viewing conditions. Here's how it works. Comets shed dust continuously as they orbit, and that dust doesn't vanish instantly. It spreads out along the comet's orbital path, forming a thin sheet that extends both ahead of and behind the comet's current position. Usually, we view this from an angle where the dust sheet looks like a normal tail streaming away. But if Earth happens to cross the plane of the comet's orbit or get very close to it, we end up looking edge and through that dust sheet. From that perspective, the dust ahead of the comet becomes visible as a bright line pointing sunward, even though it's not actively being pushed in that direction. It's a line-of-sight effect, a trick of geometry where we're seeing material that's actually moving away from us, but appears to point forward because we're looking through it sideways. This explanation works beautifully for many comets. In fact, several well-documented cases of antitails have been fully explained by this geometry. The problem is that 3I Atlas doesn't fit the pattern cleanly. Astronomers have run the numbers. They've calculated the orbital plane, plotted Earth's position relative to the comet throughout the observation period, and modelled how a dust sheet would appear from our vantage point. And while there's some alignment, enough to create a weak antitail effect, it's not enough to explain the brightness and sharpness of what's actually being observed. The forward structure is too prominent. It's not the faint, diffuse glow you'd expect from scattered light through a thin dust sheet. It's a distinct, well-defined feature, almost as bright as the main tail in some images. That suggests something more substantial than a geometric illusion. It suggests actual material, concentrated and reflective, positioned ahead of the comet's nucleus in a way that resists easy explanation. Then there's the issue of persistence. Antitails from dust sheets tend to come and go as the viewing geometry changes. A few degrees of shift in Earth's position relative to the comet's orbit can make the effect vanish or reappear. But 3I Atlas's forward glow has remained visible throughout the entire observation window, from mid-November through early December, even as the angles have changed. That consistency argues against a purely geometric effect. It suggests that whatever is creating that glow is physically there, moving with the comet, not just a fleeting alignment of viewpoint and dust. And that's when researchers started considering alternatives. What if the antitail isn't dust at all? What if it's solid objects, fragments, chunks, maybe even intact smaller bodies, travelling ahead of the comet, bound to it by gravity, and reflecting sunlight off their surfaces? What if 3I Atlas is dragging a retinue of material with it, a cloud of unknowns that formed during its journey through interstellar space, or broke off from the main nucleus during a violent event earlier in the comet's history. This is where the swarm hypothesis begins to take shape, and it's not as far-fetched as it might sound. Comets do fragment. They break apart from thermal stress, from tidal forces when passing close to massive bodies, from internal pressure as gases build up beneath the surface. When fragmentation happens, the pieces don't instantly disperse. They stay relatively close together, held by the weak gravity of the largest fragment and moving along nearly identical trajectories. Over time, some fragments drift apart, but others can remain clustered for years, even decades. If 3I Atlas underwent fragmentation at some point in its interstellar journey, perhaps during a close pass by another star, or from a collision with debris in the void, it could very well be travelling with a cloud of its own fragments. Those fragments, if they're large enough and reflective enough, would show up as a bright structure in telescopic images. And if they're positioned ahead of the nucleus due to slight differences in velocity or trajectory, they would create the exact appearance we're seeing, a forward-pointing glow that doesn't behave like gas or fine dust. But there's another layer to this, one that makes the situation even more intriguing. Observers have also noted jets on 3I Atlas, discrete plumes of gas and dust erupting from specific points on the nucleus. These jets are common on active comets. They're caused by localized venting as subsurface ices are exposed to sunlight. But jets also exert force, like tiny rocket engines, and that force can push material in directions that don't align neatly with the sun's radiation pressure. If a jet is firing in the right direction at the right intensity, it could, in theory, loft material forward, ahead of the comet, where it might linger in a semi-stable configuration. Combine that with the possibility of pre-existing fragments, and you have a scenario where the forward glow is neither purely geometric nor purely new. It's a hybrid, a mix of ejected material and older debris, all clustered together in a way that amplifies the visual effect. The uncertainty here is genuine. No one is standing on solid ground with a definitive explanation. The data is ambiguous, the models are stretched, and the observations are too limited to resolve individual objects within the antitail, assuming they exist. What we have is a mystery anchored in real measurements, brightness curves, spectral data, positional tracking, but open to multiple interpretations. And that's exactly the kind of situation where bold hypotheses emerge, where researchers willing to stick their necks out start proposing ideas that sound speculative but are grounded in the math and physics of what's being observed. One of those researchers is Avi Loeb, and his take on the 3I Atlas antitail is where the swarm hypothesis goes from intriguing possibility to headline-grabbing claim. Let's turn our attention there now. If you follow space news with any regularity, you've heard the name Avi Loeb. He's a professor of astrophysics at Harvard, former chair of the university's astronomy department, and someone whose career has been marked by both prestigious contributions to theoretical astrophysics and a willingness to entertain ideas that make his colleagues deeply uncomfortable. He's the scientist who suggested that Oumuamua, the first confirmed interstellar object, might have been an alien probe, a claim that ignited fierce debate and positioned him as either a visionary willing to follow evidence wherever it leads, or a provocateur chasing headlines depending on who you ask. Love him or dismiss him, Loeb has a track record of taking data seriously and proposing explanations that prioritize observational fit over conventional comfort. And now he's turned his attention to 3I Atlas and its antitail, and what he's proposing is both scientifically grounded and unsettling in its implications. In a recent essay released just days ago, Loeb laid out a hypothesis that cuts through the hand-wringing over dust geometry and viewing angles. He suggests that the antitail of 3I Atlas is not an illusion, not a trick of light, and not a sheet of scattered dust. Instead, he proposes that it's a swarm, a cluster of solid objects gravitationally bound to the comet's nucleus, travelling ahead of the main body in a relatively stable configuration. These objects, according to Loeb, are reflecting sunlight off their surfaces, creating the bright forward glow that telescopes are capturing. The key distinction in his model is that these aren't gas molecules or microscopic dust grains being blown around by radiation pressure. They're substantial chunks, possibly fragments from the comet's own past fragmentation, possibly material that accreted onto the comet during its interstellar journey, possibly something else entirely, but large enough and numerous enough to produce a coherent observable structure. And because they're gravitationally bound, they move with the comet, maintaining their position ahead of the nucleus instead of dispersing into space the way loose dust would. Loeb's model hinges on a few critical points. First, he notes that the brightness and sharpness of the antitail are consistent with reflected sunlight off solid surfaces, not emission from gas or scattering from fine dust. Spectroscopic data, while limited, doesn't show the signatures you'd expect from active outgassing in that region. There's no strong emission line from ionized gas, no clear evidence of sublimation. What you see is more consistent with passive reflection, light bouncing off solid material. Second, the stability of the structure suggests gravitational coherence. If the antitail were purely geometric, a line-of-sight effect through a dust sheet, it would fluctuate as the viewing angle changed. But it doesn't. It persists, which implies that the material creating it is physically there, moving in lockstep with the comet. Third, the position of the swarm ahead of the nucleus makes sense if you think about how fragmentation works. When a comet breaks apart, the fragments don't all move at exactly the same speed. Some get a slight velocity boost from outgassing or rotational forces. If those fragments end up moving slightly faster than the main nucleus, they'll drift ahead over time, settling into a leading position. From Earth, that would appear as a forward glow, exactly what we're seeing. Now, Loeb is careful to label this as a hypothesis, not a proven fact. He acknowledges that the data is limited, that resolution is insufficient to confirm individual objects, and that alternative explanations haven't been ruled out. But he also argues that the swarm model fits the observations better than the alternatives currently on the table, and that it deserves serious consideration and targeted follow-up observations. He's calling for high-resolution imaging campaigns, spectroscopic analysis of the antitail region, and even attempts to detect individual objects within the swarm if they're large enough to resolve. In other words, he's not just throwing out a wild idea and walking away, he's proposing a testable hypothesis and outlining the steps needed to confirm or refute it. That's how science is supposed to work, even when the hypothesis makes people uneasy. But here's where it gets more complicated. Loeb doesn't stop at suggesting the swarm is made of natural fragments. He opens the door, carefully, cautiously, but unmistakably, to the possibility that some of the objects in the swarm might not be natural at all. He doesn't claim they're artificial. He doesn't say they're alien probes or spacecraft. He simply notes that if you're dealing with an interstellar object, something that has travelled for potentially millions of years through the galaxy, possibly passing near other star systems, possibly encountering environments and forces we can't replicate or fully model, you can't rule out the presence of material that's been shaped by processes we don't understand. He points to the precedent of Oumuamua, which exhibited acceleration that couldn't be explained by standard comet outgassing, and suggests that interstellar objects might carry surprises precisely because they've experienced conditions outside the narrow band of environments we've studied within our own solar system. It's a subtle argument, one that stops short of making extraordinary claims but gestures in that direction, and it's this aspect of Loeb's work that draws both fascination and criticism. Critics argue that Loeb is too quick to jump to exotic explanations when simpler ones haven't been exhausted. They point out that antitails are known phenomena, that dust geometry can be tricky, and that invoking swarms of unknown objects without direct evidence is premature. They worry that his high profile and willingness to engage with speculative ideas gives undue weight to hypotheses that should remain in the realm of interesting but unproven, rather than being elevated to public discussion. And there's a fair point buried in that criticism. Science progresses through conservative steps, gather data, test simple models, add complexity only when necessary. Leaping to swarms and hinting at non-natural origins before exhausting natural explanations can muddy the waters and make it harder to separate signal from noise. But Loeb's defenders, and there are many, even among those who disagree with his specific claims, argue that his willingness to push boundaries is exactly what's needed when dealing with objects we've literally never encountered before. Interstellar visitors are, by definition, outside our experience. We have no direct data on how they form, how they weather, what they carry, or how they behave under stress across light years of travel. Every assumption we make is based on solar system objects, which might be a poor analogue. In that context, entertaining bold hypotheses isn't recklessness, it's intellectual honesty. It's an acknowledgement that we don't know what we don't know, and that sometimes the only way to make progress is to propose ideas that feel uncomfortable, and then design observations to test them rigorously. That's the approach Loeb is advocating for 3i Atlas. Not blind acceptance of the swarm hypothesis, but serious, funded, sustained efforts to determine whether it's correct. And if it turns out he's wrong, that's fine. That's how science works. But if he's right, even partially, then we're looking at something genuinely new, and the implications ripple outward in ways we're only beginning to consider. One of those implications is the question of what, exactly, would fill such a swarm if it exists. What kinds of objects could survive the interstellar journey, cluster together gravitationally, and reflect sunlight in the way we're observing? That's not a trivial question, and the answers range from straightforward to deeply strange, which is where we need to go next. Imagine you're holding a handful of gravel. Now imagine that gravel has been travelling through the void between stars for 1 million years, bombarded by cosmic rays, frozen to near absolute zero, exposed to radiation from distant suns, and never once touched by an atmosphere or a gravitational field strong enough to pull it together into a planet. What would that gravel look like? How would it behave? Would it still be recognizable as rock, or would it have transformed into something stranger? Glass, crystal, fused metal, organic compounds polymerized into forms we've never seen in a lab. That's the thought experiment at the heart of the swarm question. If 3i Atlas is carrying a cluster of objects, we need to ask not just how many or how large, but what they're made of and how they came to be travelling with the comet in the first place. The answers span a wide spectrum, from the comfortingly mundane to the genuinely unsettling. Let's start with the natural, straightforward explanations, because these are the ones most scientists default to, and for good reason. They don't require invoking new physics or exotic processes. The simplest scenario is that the swarm consists of fragments from the comet itself, pieces that broke off during a past event and have been travelling in close formation ever since. Comets fragment all the time. Thermal stress from repeated heating and cooling as they orbit stars can crack the nucleus. Tidal forces from close passes by massive objects can literally rip a comet apart. Internal pressure from sublimating gases can cause explosive outbursts that shatter sections of the surface. If 3i Atlas underwent any of these events during its interstellar journey, and it's plausible, given that it likely spent time in the vicinity of other stars before arriving here, it could easily have shed fragments that remained gravitationally bound. These fragments would be ice and rock, similar in composition to the main nucleus, ranging in size from boulders to small hills. They'd reflect sunlight efficiently if their surfaces were relatively fresh and unweathered, which could explain the brightness of the antitail, and they'd cluster ahead of the nucleus if they received even a slight velocity boost during the fragmentation event, settling into a leading position over time as gravity kept them from dispersing completely. This model is tidy. It requires no new assumptions about interstellar material or exotic processes. It's just standard comet physics applied to an object that happens to have an interstellar origin. And it fits a lot of the observational data. The brightness, the persistence, the rough geometry, all of it works if you assume a swarm of comet fragments reflecting sunlight. The main challenge is resolution. Telescopes on Earth, even the most powerful ones, can't yet resolve individual objects within the antitail at the distance 3i Atlas has travelled. We see a bright glow, not discrete points of light, so confirming the fragment hypothesis would require either much higher resolution imaging, possibly from space-based telescopes or future missions, or indirect evidence like spectroscopy, showing that the antitail region has the same composition as the nucleus, which would support the idea that it's made of the same material. But there's a second natural scenario that's less tidy and more intriguing. What if the swarm isn't fragments from 3i Atlas, but material it picked up during its interstellar journey? Interstellar space isn't empty. It's filled with gas, dust, and larger debris, remnants of dead stars, particles ejected from planetary systems, and material that's been drifting for eons. A comet travelling through this environment at high speed would encounter some of this material. Most of it would collide and either stick to the surface or bounce off, but there's a possibility that larger chunks, maybe clumps of dust or small icy bodies, could be captured by the comet's gravity if the encounter happened at just the right velocity and angle. Over thousands or millions of years, a comet could accumulate a retinue of such objects, a collection of hitchhikers bound loosely by gravity and travelling in formation. This accreted material wouldn't necessarily match the comet's original composition. It could be richer in metals if it formed near a different type of star. It could contain organic compounds or mineral structures we don't see in solar system objects. It could, in theory, be identifiable as foreign even if we can't resolve individual pieces, because the spectroscopic signature would differ from the nucleus. This accretion scenario is speculative, but it's not wild speculation. We know that objects in space do capture material. Planets sweep up dust. Asteroids collide and stick together. The question is whether a small, fast-moving comet in interstellar space could accumulate enough material to create a visible swarm, and whether that material would stay bound over the timescales involved. The math is uncertain. Gravity weakens with distance, and a comet nucleus only a few miles across has incredibly weak gravity, barely enough to hold its own surface together, let alone capture and retain foreign objects, but it's not impossible, especially if the captured material is moving at very low relative velocity when the encounter happens. And if 3I Atlas did pick up hitchhikers, then the swarm we're seeing might be a sample of interstellar material from multiple sources, a composite object carrying pieces of different environments, different stars, different histories. That would make it scientifically invaluable, a mixed archive of the galaxy's material diversity delivered to our doorstep for study. Now let's move into more speculative territory, the kind of ideas that make most scientists squirm, but that can't be dismissed outright given how little we know about interstellar objects. What if some of the objects in the swarm aren't fragments or accretions but something else? Material that's been processed, shaped, or structured in ways we don't associate with natural comet behaviour? I'm not talking about alien spacecraft. I'm talking about objects that might have undergone physical transformations during their journey, that leave them looking unusual or behaving in unexpected ways. For example, prolonged exposure to cosmic rays and radiation can alter the surface chemistry of ice and rock, creating compounds and structures that don't form under normal solar system conditions. You could end up with surfaces that are unusually reflective, or that sublimate at unexpected rates, or that have crystalline structures we'd classify as anomalous if we saw them in a lab. These wouldn't be artificial, but they'd be strange, natural objects shaped by unnatural, from our perspective, environments. There's also the question of density and composition. Interstellar space is mostly hydrogen and helium, but there are regions, near star-forming clouds, near supernova remnants, where heavier elements are more abundant. A comet passing through such a region could, over time, accumulate a coating of unusual material, metals, complex organics, even radioactive isotopes if it passed near a supernova. If fragments broke off later, they'd carry that unusual coating with them. Viewed from Earth, such objects might have spectral signatures that don't match anything we've catalogued. They'd be natural but exotic, and identifying them correctly would require rethinking our assumptions about what interstellar material looks like. This isn't science fiction. This is the frontier of astrochemistry and planetary science. The recognition that the conditions out there between stars are vastly more varied than the narrow band of environments we experience in our solar system, and that objects shaped by those conditions might not fit our categories neatly. And then, because we're being honest about the full spectrum of possibilities, there's the whisper in the room that no one wants to say too loudly, but that keeps surfacing in comment sections, in fringe discussions, in the more speculative corners of the scientific community. What if some of the objects in the swarm are not natural at all? What if they're manufactured, designed, intentionally placed? I want to be crystal clear here. There is zero direct evidence for this. None. No signals, no unusual materials, no structural anomalies that scream artificial. But the reason this idea keeps coming up isn't pure fantasy. It's because Oumuamua set a precedent. When that object accelerated without visible outgassing, conventional explanations struggled. Loeb proposed that it might be a light sail, a thin reflective structure accelerated by radiation pressure, possibly of artificial origin. The idea was widely criticised, but it also couldn't be definitively ruled out because we didn't have enough data. Now we have another interstellar visitor exhibiting unusual behaviour, and the same questions arise. If you're an advanced civilization looking to explore or sample other star systems, sending probes attached to comets would be a smart strategy. Comets are common, they travel between stars naturally, and they provide a gravitational anchor for lightweight probes or instruments. A swarm of small objects travelling with a comet would be easy to miss unless you were looking closely. And if you were looking closely, you might dismiss it as natural fragmentation unless you could get close enough to resolve details. Again, no evidence supports this. It's pure speculation, the kind of thing that belongs in the interesting to think about but not actionable category. But it's not crazy. It's a logical extension of the idea that other civilizations might exist and might explore using methods we'd find clever if we thought of them ourselves. And the reason it's worth mentioning at all is that it frames the stakes. If the swarm is natural fragments or accretions, that's scientifically valuable, but not paradigm-shifting. If it's exotic material shaped by rare interstellar processes, that's more interesting, potentially opening new avenues of research. But if even one object in that swarm turned out to be artificial, even if it's just a simple probe or sensor, that changes everything. That means we're not alone, that we're being watched or at least sampled, and that the galaxy is far more active and interconnected than we imagined. It's an infinitesimally small probability, but it's not zero, and that non-zero status is enough to keep the question alive in the minds of researchers and enthusiasts alike. So what could fill this swarm? The most likely answer is natural fragments, ordinary comet debris gravitationally bound and reflecting sunlight. The next most likely is accreted material, hitchhikers picked up during the interstellar journey. Further down the probability ladder are exotic natural objects shaped by rare processes, and at the very bottom, but still present, is the artificial hypothesis. All of these are on the table because the data doesn't yet allow us to rule any of them out definitively, and that ambiguity is precisely why the swarm hypothesis, whether you buy into it or not, is driving so much attention right now. It's a mystery with multiple solutions, and the only way to narrow them down is through better observations, more data, and rigorous analysis. But not everyone agrees that the swarm hypothesis is even necessary, and that's where the scientific debate gets sharp. Science thrives on disagreement. It's not a weakness, it's the engine of progress. When a bold hypothesis like Loeb's swarm model hits the community, the response isn't universal acceptance or rejection. It's a clash of interpretations, methods, and standards of evidence. And right now, the pushback against the swarm hypothesis for 3i Atlas is vigorous, detailed, and worth taking seriously because it exposes the gaps in our current understanding and forces everyone to sharpen their arguments. The skeptics aren't dismissing the mystery. They're questioning whether we need to invoke a swarm at all to explain what we're seeing, or whether more conventional mechanisms can do the job if we apply them carefully. This is the scientific method in action: propose, challenge, test, refine. And the challenges being raised are not trivial. The first line of criticism focuses on the geometry explanation, the idea that the antitail is a line-of-sight effect through a dust sheet rather than a cluster of discrete objects. Critics of the swarm hypothesis argue that while the viewing angle for 3i Atlas isn't perfect for producing a classic antitail, it's close enough that with some adjustments to the dust model, accounting for variations in dust size distribution, density gradients, and the specific timing of dust ejection events, you can reproduce the observed brightness and sharpness without invoking a swarm. They point to detailed simulations of comet dust behavior that show how even a thin sheet of dust, if viewed edge-on, can produce sharp, bright features that look nothing like the diffuse glow most people associate with tails. The key variable in these simulations is the size of the dust particles. Larger grains, pebbles and small rocks, not just microscopic dust, are less affected by radiation pressure and settle into tighter, more stable configurations along the comet's orbit. If 3i Atlas has been shedding larger particles at a higher rate than typical comets, those particles would create a denser, brighter dust sheet that could easily explain the antitail without requiring gravitationally bound fragments. This is a powerful counterargument because it doesn't require new assumptions. It's just standard comet physics applied more carefully. And it has precedent. Several comets with prominent antitails have been fully explained by dust geometry once the models were refined to match the specific characteristics of the comet and the viewing conditions. The challenge for the swarm hypothesis is to demonstrate that the geometry explanation, even when optimized, still falls short, that there's something in the data that can't be explained by dust alone. So far, that definitive proof hasn't materialized. The brightness is suggestive, the sharpness is intriguing, but neither is conclusive. And that leaves room for skeptics to argue that the swarm model is premature, a leap to complexity when simplicity might still work. The second line of criticism targets the stability argument. Loeb's model suggests that the swarm is gravitationally bound, held together by the comet's weak gravity as it travels. But several researchers have run the numbers on this and they're skeptical. The gravitational pull of a comet nucleus a few miles across is incredibly weak, far weaker than the perturbations caused by solar radiation pressure, the solar wind, and even the comet's own outgassing jets. For fragments to remain clustered ahead of the nucleus over weeks or months, they'd need to be moving at almost exactly the same velocity as the nucleus, and they'd need to avoid being pushed apart by all the forces acting on them. That's a delicate balance, and it's not clear that it's stable over the timescales involved. Simulations of comet fragmentation show that while fragments do stay together initially, they tend to drift apart over time, dispersed by even small velocity differences and external forces. The fact that 3I Atlas's anti-tail has remained stable throughout the observation period is seen by some as evidence against a swarm, not for it, because a true swarm should show signs of dispersion, brightening or fading, spreading or concentrating, as the fragments move relative to each other and relative to Earth. The lack of such changes suggests a more static structure, which fits better with a geometric dust effect than with a dynamic collection of objects. Then there's the spectroscopic critique. If the anti-tail is made of solid fragments, those fragments should have a spectral signature distinct from fine dust. Solid objects reflect sunlight differently than clouds of tiny particles. The reflection is more directional, the colour distribution is different, and there should be detectable differences in how polarised the light is. Several observatories have attempted spectroscopic measurements of the anti-tail region, and while the data is noisy and limited, the preliminary results don't show strong evidence for solid body reflection. The light looks more consistent with scattered sunlight from dust, not mirrored reflection from rocky or icy surfaces. That doesn't rule out a swarm. Solid fragments covered in dust would look dusty, but it weakens the case. If the swarm exists, it's not revealing itself in the ways we'd expect based on how solid objects behave in space. There's also a metacriticism directed more at the messenger than the message, and while it's uncomfortable, it's part of the conversation. Avi Loeb has a reputation for pushing speculative ideas, and that reputation colours how his proposals are received. Some scientists argue that his willingness to entertain exotic explanations, especially those with even a hint of non-natural implications, lowers the bar for what counts as a serious hypothesis. They worry that by giving airtime to the swarm model before exhausting simpler explanations, the community risks chasing headlines rather than following the data. It's a harsh critique, and it's not entirely fair. Loeb has been clear that his hypothesis is testable, and that he's calling for more observations, which is exactly what responsible science looks like. But the concern isn't entirely baseless either. The line between bold thinking and sensationalism can be thin, and in an era where scientific findings are amplified through social media and press releases before peer review has even begun, there's a legitimate worry about ideas gaining traction based on their novelty rather than their evidential support. Yet for all this pushback, the skeptics aren't claiming the mystery is solved. They're not saying the anti-tail is boring or fully understood. What they're saying is that we need to be careful, methodical and conservative in how we interpret ambiguous data. They're advocating for a hierarchy of explanations, exhaust the simple before embracing the complex, confirm the natural before considering the exotic, and demand high-quality evidence before making claims that will reverberate beyond the astronomy community. And that's a reasonable standard. It's how science is supposed to work. The tension between Loeb's boldness and the skeptic's caution isn't a flaw in the process. It's the process functioning as designed. One side pushes the boundaries, proposing ideas that stretch the data. The other side pushes back, demanding rigour and proof. And somewhere in the middle the truth emerges, not through consensus, but through the accumulation of evidence that eventually forces everyone to agree. So where does that leave us right now with 3I Atlas? It leaves us in a state of productive uncertainty. The swarm hypothesis is on the table, supported by suggestive observations but not confirmed. The geometry explanation remains viable, challenged by some data but not ruled out. And the community is actively gathering more information, scheduling telescope time, processing images, and running models to test which explanation fits better. This isn't a stalemate. It's active science in the messy middle stage where questions outnumber answers. And that's exactly the moment when we need to look closely at what the data actually shows, Not what we hope it shows, not what would make the best story, but what the light and shadows of 3i Atlas are actually telling us. Let's talk about what we can see and what we can't, because that distinction is everything in this debate. Astronomy is fundamentally the science of interpreting light. We can't touch 3i Atlas. We can't send a probe to it, not yet, not with current technology, not before it leaves the solar system forever. All we have is the light it reflects, the tiny fraction of sunlight that bounces off its surface and travels across millions of miles to reach our telescopes. And from that light, we have to reconstruct not just what the object looks like, but what it's made of, how it's moving, and whether it's carrying anything with it. It's detective work at cosmic scale, and right now the clues are both tantalizing and frustratingly incomplete. Start with the images themselves. The best photographs of 3i Atlas come from large observatories using long exposure techniques, where multiple images are stacked together to enhance faint details and reduce noise. In these stacked images, the comet's nucleus appears as a bright point, slightly elongated, surrounded by a diffuse glow from the coma, the cloud of gas and dust immediately around the nucleus. Stretching away to the left in most images is the main dust tail, broad and faint, arcing gently as it follows the comet's orbit. And then, stretching in the opposite direction, forward toward the sun, is the antitail. It's narrower than the main tail, brighter relative to its width, and remarkably straight. It doesn't curve, it doesn't fan out. It looks almost laser-like in some exposures, a sharp spike of light that seems to defy the softness of everything else in the image. That sharpness is one of the first clues that something unusual is going on. Sharpness in astronomical images typically indicates one of two things. Either you're looking at a very thin structure aligned perfectly with your line of sight, or you're looking at discrete objects that aren't diffusing into a cloud. The geometry explanation interprets it as the first, a thin dust sheet seen edging. The swarm hypothesis interprets it as the second, a cluster of objects reflecting light in a concentrated area. Both interpretations fit the shape, but they predict different behaviors when you look at how the brightness changes over time. If it's geometry, the brightness should vary as the viewing angle changes, fading when Earth moves out of alignment with the dust sheet. If it's a swarm, the brightness should stay relatively constant as long as the swarm stays together, because you're seeing reflected sunlight from solid surfaces, which doesn't depend as much on viewing angle. Observers have been tracking the antitail's brightness across multiple nights, and the data shows stability. The feature doesn't flicker, doesn't fade significantly, doesn't change shape dramatically. It's persistent. That's a point in favour of the swarm hypothesis, but it's not definitive, because a dense dust sheet can also be stable over short timescales. Then there's the question of spectroscopy, which should be the smoking gun one way or the other, but so far has been inconclusive. Spectroscopy splits light into its component wavelengths, revealing the chemical fingerprints of whatever is emitting or reflecting that light. If the antitail is made of gas, you'd see emission lines, bright spikes at specific wavelengths corresponding to excited molecules like water vapour, carbon monoxide or hydroxyl radicals. If it's dust, you'd see a continuous spectrum, the rainbow of reflected sunlight, maybe with absorption features if certain minerals are present. If it's solid objects, you'd expect strong reflection at visible wavelengths, possibly with variations in colour depending on the surface composition. Several teams have attempted spectroscopic observations of the antitail, but the results are noisy. The feature is faint, and teasing out its spectrum from the surrounding glow of the main tail and coma is technically challenging. Preliminary data leans toward a continuous spectrum consistent with reflected sunlight, which fits both dust and solid objects. There's no strong emission, which argues against active gas release in that region, but there's also no clear indication of solid body reflection, no strong colour shifts or polarization signatures that would confirm fragments. It's consistent with both models, which means it doesn't help resolve the debate yet. What about attempts to resolve individual objects? This is where current technology hits its limits. The angular resolution of even the best ground-based telescopes accounting for atmospheric distortion is measured in fractions of an arcsecond. At the distance 3i Atlas was during peak observation, roughly a few 100 million miles, 1 arcsecond corresponds to hundreds of miles on the sky. The antitail spans a distance of thousands of miles, but individual fragments, if they exist, would be much smaller, maybe tens or hundreds of feet across. To resolve such objects, you'd need either a space-based telescope with adaptive optics, or you'd need the comet to be much, much closer. Neither is currently available, so when we look at the antitail, we see an integrated glow, the combined light from whatever is out there, but we can't pick out individual pieces. It's like looking at a distant city at night. You see the glow of streetlights, but you can't make out individual lampposts. The swarm could be there, but it's below our resolution threshold. There's another technique that might help, analysing how the brightness varies across the length of the antitail. If it's a uniform dust sheet, the brightness should drop off smoothly with distance from the nucleus, following predictable curves based on how dust disperses. If it's a swarm of discrete objects, the brightness might be clumpier, with peaks and valleys corresponding to where fragments are concentrated. Researchers have been doing this kind of photometric analysis, measuring brightness profiles along the antitail, and the results are messy. There are hints of clumpiness, regions where the glow seems slightly brighter or dimmer than the average. But the noise in the data is high enough that you can't say definitively whether those variations are real structure or just statistical fluctuations. It's suggestive but not conclusive. The pattern you'd expect from a swarm is sort of there, but not strongly enough to rule out other explanations. And then there's the timing factor. Right now, as we speak, 3i Atlas is moving away from both the Sun and Earth, and it's fading. The window for high-resolution observations is closing. Each day that passes, the comet gets dimmer and harder to study. The antitail is still visible in the latest images, but it's weaker, and soon it will drop below the detection threshold of all but the most powerful telescopes. If we're going to confirm the swarm hypothesis, or rule it out, it has to happen soon, within weeks at most, before the comet recedes beyond the point where detailed measurements are possible. That urgency is driving a lot of the current activity. Observatories that wouldn't normally dedicate time to a single object are making exceptions. Amateur networks are coordinating their observations to maximize coverage. And researchers are processing data in real time, sharing preliminary findings before formal publication, because waiting months for peer review could mean missing the opportunity entirely. What we're looking at here is a case study in the limits of observational astronomy. We have enough data to know something interesting is happening, enough to rule out some explanations and support others weakly, but not enough to close the case. The antitail is real, it's anomalous, it fits the swarm hypothesis in some ways and challenges it in others. The geometry explanation still works if you tweak the parameters, but it feels like a stretch in places, and the spectroscopic and photometric data are too ambiguous to definitively favour either side. We're in that frustrating zone where the evidence is intriguing but not conclusive, where smart people can look at the same data and reach different conclusions based on which uncertainties they're willing to tolerate. It's uncomfortable, especially for those of us who want clear answers, but it's also the reality of doing science at the edge of our capabilities. Sometimes the universe hands you a mystery, and all you can do is gather every clue you can before the opportunity slips away. And that's exactly what's happening now with 3i Atlas, a race against time and distance to extract as much information as possible from a visitor that will never return, knowing that what we learn might reshape how we think about the space between stars and what it carries. But even if we never confirm the swarm, even if it turns out to be an exceptionally strange dust configuration and nothing more, the stakes of this investigation reach far beyond one comet. The questions raised by 3i Atlas about what interstellar objects carry, how they behave, and what we should look for, have implications that ripple across astronomy, planetary defense, and even our broader search for life and intelligence in the cosmos. That bigger picture is where we turn now. Step back from the telescopes for a moment and think about what this really means. We're not just talking about one comet with a strange tail. We're talking about the first time in human history that we've had the tools, the awareness, and the opportunity to study interstellar visitors as they pass through our solar system in real time. Every object that crosses the boundary from interstellar space into our sun's domain carries information about the star systems it came from, about the processes that shaped it, about the diversity of materials and structures that exist across the galaxy. We've confirmed exactly 3 of these visitors so far. 3 data points. That's not a sample. It's barely a hint. And yet each one has surprised us, challenged our models, and forced us to expand our thinking about what's possible. Oumuamua accelerated mysteriously. Borisov showed unusual activity patterns. Now 3i Atlas glows where it shouldn't. If we're being surprised this consistently with such a tiny sample, what does that tell us about how much we don't know? The swarm hypothesis, whether it's confirmed or not, represents a shift in how we think about these objects. Traditionally, we've treated comets as isolated bodies, chunks of ice and rock following predictable paths, behaving according to well-understood physical laws. But 3i Atlas is pushing us to consider the possibility that interstellar objects might be more complex, more composite. Maybe they don't travel alone. Maybe they accumulate companions during their journeys, picking up fragments and debris, becoming loose aggregates held together by weak gravity. Maybe fragmentation is more common than we thought, and what we call a comet is often really a cluster of pieces moving in formation. If that's true, then every future interstellar visitor might carry a swarm of its own, and we need to design our observation strategies accordingly. We need to look not just at the main nucleus, but at the surrounding space, watching for secondary structures, faint glows, anything that suggests additional material travelling in formation. The swarm hypothesis, even if it's wrong for 3i Atlas, might still be teaching us what to look for next time. There's also a planetary defence angle here that's easy to overlook but critically important. We spend a lot of effort tracking near-Earth objects, asteroids and comets that could pose a collision threat to our planet. But all of that effort is focused on objects that belong to our solar system, objects whose orbits we can predict decades or centuries in advance. Interstellar visitors are different. They come from outside, following paths we can't predict until they're already here, moving at speeds higher than anything native to our system. If an interstellar object were on a collision course with Earth, we'd have very little warning and almost no ability to deflect it with current technology. Now add the swarm factor. If interstellar objects routinely travel with clusters of fragments, then a single detected comet might actually represent multiple impact threats, a spread of smaller bodies that could hit different parts of the planet. That's not a scenario anyone wants to contemplate, but it's one we need to be prepared for as we learn more about how these visitors behave. Understanding whether 3i Atlas carries a swarm isn't just academic curiosity, it's foundational knowledge for assessing the risks posed by future interstellar arrivals. And then there's the bigger existential question, the one that hovers at the edges of every discussion about interstellar objects even when people don't say it out loud. If material can travel between stars naturally, carried by comets and ejected planets, and who knows what else, then the galaxy is more interconnected than we usually imagine. Material from one star system ends up in another. Organic molecules, maybe even primitive life, could be distributed across light years. The building blocks of planets, the seeds of biology, might not be confined to their birthplaces but spread through the galaxy by these wandering objects. Every interstellar visitor is a sample return mission we didn't have to launch, delivering material from distant systems directly to our instruments. And if that's true, then every swarm, every fragment, every chunk of ice and rock riding with these comets is a message from elsewhere. Not an intentional message, but a record of conditions, chemistry, and history from places we'll never visit. The possibility, however remote, that some of those fragments might not be natural adds another layer entirely. We have no evidence for artificial objects in the 3i Atlas swarm. None. But the lack of evidence isn't the same as evidence of absence, especially when our instruments can't yet resolve individual objects within the anti-tail. If even one advanced civilization in the history of our galaxy decided to explore by sending probes attached to comets, riding the natural flow of material between stars, then statistically some of those probes might still be out there, drifting, waiting to be noticed. The odds are low, the timescales are vast, but the possibility is non-zero, and that changes how we look at every interstellar visitor. We can't afford to assume everything is natural without checking. We need to look closely, image carefully, and stay open to the idea that the universe might surprise us in ways we haven't imagined yet. That's not wild speculation. That's basic due diligence in an era where we know interstellar objects exist, and we're just beginning to study them seriously. So here's where we are. 3i Atlas is fading. The observations are winding down. In a few weeks, it will be too dim to study with anything but the most powerful space telescopes, and even those will struggle. The swarm hypothesis remains unproven, but it's not disproven either. The anti-tail is real, anomalous, and poorly understood. The debate between dust geometry and gravitationally bound fragments continues, and both sides have valid points. What we've learned from this visitor is that interstellar objects are more complex and less predictable than we hoped. They don't fit neatly into our categories, they challenge our instruments and our models, and they remind us that the space between stars is not empty, not simple, and not fully mapped. Whatever rides with 3i Atlas, whether it's dust, fragments, or something stranger, it's teaching us what to look for in the next visitor and the one after that. We're building a catalogue of interstellar behaviour, one object at a time, and every anomaly is a clue. If you've stayed with me this long, you care about these questions. You care about what's out there, what's passing through, and whether we're seeing everything we should be seeing. So keep watching, follow the updates as new data comes in, question the headlines, demand the evidence, and stay critical of both bold claims and comfortable explanations. The universe doesn't owe us easy answers, and the best discoveries often come from things that don't make sense at first. 3i Atlas and its mysterious anti-tale might be a footnote in astronomy textbooks, or it might be the first chapter in a much stranger story. Either way, we're watching it unfold in real time, and that makes you a witness to something rare. Don't look away. The swarm, if it's there, is slipping through our solar system right now, carrying secrets from the stars, and we might never get this close again.